Hello, everyone. So first, I will introduce myself. So now I'm the senior cybersecurity researcher and at CyCraft. So the same as the last talk. And we are from Taiwan. And I mainly focus on the malware analysis and sandbox development. And I have also published in some conference before. And I have participated in some CTF and in DEFCON. Okay, so first, as we all know, the APT threats are very serious, and the APT group often stay hidden in the system for a long time. So you may wonder why the APT can stay hidden for so long. And especially since most organizations now has various security products installed in their system, like the EDR. So how do APT bypass the EDR detection? So in the upcoming section, I will use 3 real APT cases to show you how APT group bypass the EDR detection. And we will also categorize these different techniques. Okay, so before we dive into the APT case, here is the outline today. We will first look at the basic architecture of the EDR and discuss the pros and cons of different evasion techniques. And next, we will explore 3 real-world APT cases and to see how they evade the detection. Okay, so first we will see how the EDR works. So here, this is the basic architecture of a typical EDR system. So there are mainly 2 components here. First is there's agent and sensors. And some of the sensors are in user land like the scanner or like the API hooking. And some other sensors are inside the kernel. So agents are like the brain of the EDR, and sensors are like the eyes of the EDR. An agent will collect the telemetry from the sensor and perform some initial assessment, and then send the data back to the remote server for blue team to analyze. So if the attacker tries to be evasive, there are many 2 ways to do it. So first, they can try to kill the brain and try to kill the agent. So I call this type of method active manipulation. So because this kind of method is more aggressive and try to interfere with the agent directly. So for example, they can try to cut the network of the EDR, making the blue team unable to receive the data from the agent. Or they can try to kill the agent directly. And in some cases, we also see malware try to do API hooking inside the EDR system and try to hide its behavior. So while directly disabling the EDR is simple and effective, it can easily attract the attention to blue team because they may notice that the endpoint is offline and they start to begin investigate what happened. So instead of active manipulation on the agent, the attacker can try to avoid being seen by the sensor. So this is a more stealthy way to evade the detection. In this kind of method, the attacker needs to know what the EDR is monitoring and evade each sensors accordingly. So for example, the attacker can try to evade the API hooking by using direct syscall. Or they can try to avoid the scanner by applying multi-stage loader. And this is like a cat and mouse game where each side tries to bypass other one's technique. Okay, so in addition to active manipulation and passive evasion, there are some techniques that require well study of the EDR and target specific EDR system. So based on this factor, we divide the techniques into 5 categories. So all of the list technique we list on the table, we will show in the following APT case. So you may notice that there's other category in the table. So we will see this technique in the last APT case, which involve using EDR as a phishing bait. So while this is not a traditional EDR evasion techniques, it is still quite interesting to see. So we will discuss this in the last APT case. Okay, now we can start see our first APT case. So in this case, API hooking is used against the EDR system. So here is some background. So in this case, we were the first to discover some malware and inform our related vendors. The malware is water-bear, and it employs multiple techniques to evade the detections, such as dynamic decryption to counter the memory forensic, or hooking specific function to hide its own behavior. So we have published this case before. So today we will focus on how the attacker performed the API hooking on EDR in this case. So this is the execution flow of the water-bear malware. So for the normal water-bear infection, it will try to inject its shellcode into SVC host and connect back to the C2 server. This is like a traditional malware behavior. But in this case, another shellcode has been dropped, and it will patch the EDR system to do API hooking on 3 functions: the ZW open process, the get extending TCP table, and the get RTT and hopcon. These 3 functions. So the first function it hooks is the ZW open process. When you try to access a process, you need to first call the open process and get a handle to the process. But the attacker hijacks this open request to check whether the process is one of the one they want to avoid, one of the process that malware use, and they will replace this process with another innocent process. So by doing this, EDR is unable to see the process of the malware, and it's like the process has never existed. So next, the attacker also tried to hook other 2 functions, the get extending TCP table and the get RTT and hopcon. And these two functions are related to TCP connections. And the attacker is trying to hide the TCP connection to the C2 server. So this can effectively disable the ability of the EDR to detect the network activity. Okay, so now we can conclude on the first case. Here we see that how the API hooking is used in this case. And now we're trying to hide its behavior like the rootkit. And the attacker is also familiar with the EDR system and familiar with the behavior, and specifically hook these 3 API functions that can conceal its malicious behavior. And we also see a lot of cases that the attacker try to do process injection or like DL sideloading and DL hijacking into the EDR. So we think that EDR should have some protection, like the PPL privilege or kernel module to protect its own process memory. And you also need to use something like a mini filter to prevent the DL sideloading from dropping the malware into the EDR installation folder. So at least try to protect the evasion from user land. And for attack from the kernel, we will also see some example in the next APT case. Okay, so now we will look at our second APT case. So in this case, the attacker applied multiple evasion into this endpoint. And we will spend more time to this case. So here is the overall attack path. So we are not talking too much about the first three steps. So there are two initial access points in this case because there are two different regions. And in the first region, the attacker used a leak VPN account to log into the endpoint. And on the second region, the attacker used a vulnerability on the web server and implant a Godzilla web shell. And after getting into the system, the attacker also tried to do lateral movement using tools like Evil WinRM and Impact. And now, before they run the malware and deploy the Cobalt Strike, they first try to interfere with the EDR system. So how do they interfere with the EDR system? So they use two kinds of methods. First, let's try to cut the network from the EDR, and then they try to kill the agent directly using the BYOVD technique. So here is how they cut the network. First, they change the ETC host settings on Windows. We know that ETC hosts are a map between the domain and IP. And by changing the EDR domain to an unreachable IP, this can effectively cut the network of EDR. And besides the domain, the attacker also try to blacklist the EDR IP in the firewall as well. So we can see that in the following command, use the netsh ADV firewall to add a rule in the firewall to block the EDR IP address. So this making both the domain and IP unavailable to the EDR agent. So while this is an effective approach to cut the network directly, but this might be a little obvious to touch the ETC host or to modify the firewall. And Blueprint may also notice that the EDR is offline and may start doing something. So besides cutting the network, we also find that the EDR was killed and offline. And we observed that the appearance of AMSDK drivers. And doing some investigation, we find that this AMSDK has a CVE vulnerability, which is CVE 2022-42045. And this CVE allows the attacker to do arbitrary code injection and kill the EDR in the kernel mode. So below has a link to the GitHub, and this is the POC to list CVE. So this kind of technique is called a bring your own vulnerable driver, and this is quite common method recently. The attacker will try to bring their own driver, and this driver is legitimate and has valid certificate. So with the valid certificate, the driver can be installed on the computer normally. So the user can normally install this driver without any alert. But this driver will have a vulnerability and allow the hacker to exploit and get into the kernel. So it's kind of like a handy tools for the hacker to get into the kernel. So to mitigate this kind of attack, we can add these drivers with vulnerability into blacklist. So you can find some commonly used vulnerable drivers in LOL drivers. There is an options in Windows setting that can turn on, and when you turn on, it will block commonly used vulnerable drivers. And the list is maintained by Windows, and they will regularly update the list. And it's available in Windows 10 and 11. Okay, so next we will move on to malware analysis, and we will see how evasion methods are used in this malware. So the malware uses 4 kinds of techniques to evade detection from sensors. So we will look closely at them one by one. The first method the malware uses is to bypass the detection from scanner, which is a traditional pattern matching on static binary or to scan the dynamic memory. So this is the overall execution flow of this malware. You can see that it contains multiple stages, about 4 or 5 stages, and it wants to prevent itself to be scanned and detect directly in the file system, and try to inject memory, inject itself into some other process memory. So first, the attacker uses the session env service to load a malicious DLL using photon DLL loading. So what these techniques do is basically because of the session env service relies on the TSM SISRV library, but this file path doesn't exist by default. So therefore, the attacker can place a DLL with the same name in this path, and it will be loaded by the service automatically. So there are other commonly used DLL. This is on the left. So if you place your DLL with this name in a Windows System 32 folder, so it will be loaded by the Windows service automatically. So it is quite a common used technique by the attacker nowadays. So you can try to add this DLL to your blacklist. And because this DLL by default doesn't exist on your Windows, so you can safely add it to your blacklist. And in the second stage, the encoded shellcode, the MJYZO, is decoded and will be loaded into the memory. And after that, there will be a second, the final stage, DLL will be loaded as well. And it will use the reflected DLL loading method to load the DLL into the memory. And this is a common pattern now for the attacker to encode the shellcode on the file system and load it to the memory. And because the attacker don't want the file to be detected by simple pattern matching, by simple rule from the scanner. So if you find a malicious DLL file, probably there are more related files you need to look for, and maybe they are encoded as well. So in the final stage, the attacker used process injection to insert the backdoor into the memory of a illegitimate process. So this will allow the malicious code to hide within a normal program memory. So in this case, it hides in the WMI, PRV, SC, and the runtime broker. The malware will randomly choose one of them to inject. And you may assume that actions coming from the system process are safe. But in this case, we see that the malicious DLL was injected into the normal program. So we can see that maybe some malicious activity will come in from the normal program as well. So you can try to scan the memory of the process, or try to see the memory, and you may find something interesting. Okay, so after the malware has successfully run, we found that it has also used multiple different evasion methods. And the first one is the direct syscall. And this technique is used to bypass the API hooking technique used by the EDR. And this API hooking is not like the API hooking we see in the first APT case. And in the first APT case, the attackers try to hook the function inside EDR. But here is EDR will try to hook the Windows API inside the malware. So the purpose of the APT hooking by the EDR is to record the usage of Windows API in the program. And because we know that in Windows, everything is done through the Windows API. And so knowing which Windows API the malware use can help us identify some behavior. For example, the process injection has a very clear pattern. So it will run in order of virtual allocate and write process memory, and then create remote thread. So this is a simple example of process injection. So by seeing this order of API, we can immediately find that the process is doing the process injection technique. So this is one of the telemetry will be collected by the EDR. So how does the EDR actually do the API hooking? So the EDR will inject its DLL into the target program and modify the Windows API functions inside the memory. And for example, if first two instructions in the anti-open process are push RBP and move RBP RSP, then the EDR will override them with jump instruction and to redirect the control flow to EDR function. And then it will record that this function has been called. And in addition, EDR may also record the parameter of the Windows API, which sometimes can be very useful. So there are typically two ways to evade the API hooking by EDR. So since the memory of the system library has been modified, so the first way is to recover the system library from the disk. For example, we can read the file of the NTDL on file system and write it back to the memory and to restore it. But the disadvantage is that when we try to read the NTDL file, we are still using the Windows API. So the Windows API is already hooked by EDR. So EDR will find out that you are trying to access the NTDL. So it can get alert and trying to modify back its API hooking again. So since the battle between recovering the memory of the system library is quite complex, so the other simple ways to do this is to completely give up on the Windows API. So we can do syscall directly. But syscall in Windows is a little bit different from Linux. Because in Linux, syscall number is very stable. But in Windows, the syscall number can change frequently between different versions. So that's why we need to rely on the Windows API provided by the NTDL to do the syscall in a normal situation. But luckily, we have plenty ways to find out what the syscall number is. The SSN. SSN is the syscall number. For example, like the tool SysWhisper, they have maintained a list of SSN between different versions of Windows. So we can use this maintain list to do syscall based on the different version of the target environment. Or we can, another way is we can sort the Windows API function in the NTDLL by its address. And because the address in the NTDLL is actually arranged by the order of SSN. So by simply sorting the address of the Windows API, we can immediately get a complete list of the SSN. And this is also implemented in SysWhisper 2. So you can also use this tool directly. Okay, so now we see that this malware actually implements this direct syscall method, and use this method to bypass the API hooking by the EDR. So here they try to find out the SSN by sorting the API in the NTDLL, as we mentioned before. So like in the screenshot below, it first finds the syscall number by hash of the API names. And under the hood, it will get the sorted SSN number and then set the correct SSN to RX registry. And next, it will call the syscall directly. And besides the EDR, the sandbox system also do API hooking for monitoring the malware behavior. So by doing the direct syscall, you can also bypass the sandbox detection. So how can we detect, from the blue team side, how can we detect the direct syscall? So there are two kinds of methods. So for static analysis, because the normal program won't use the syscall directly inside their program. So it is a simple pattern. We can look for the syscall instruction inside the program. So for example, we can use the obj dump tools. And these tools will dump all the instruction inside the program, and we can simply grab for the syscall. And if we find one, that this program may be malicious. Okay, so for dynamic analysis, we can also observe the call stack. And because if a program do not jump into the kernel from the NTDLL, there might be a problem. Because normal program normally will jump into the kernel from NTDLL. All the syscall is done in the NTDLL library. So if you find a program that jump into the kernel directly from its own code, so there might be a problem. So here, for example, we can use the progmon tool. Progmon can help us see the code stack. So here, the top one is the normal program. So it will call the Windows API and finally do syscall inside the NTDLL and jump into the kernel. So the last place in the user land should be in the NTDLL. But on the bottom one, the program here jump into the kernel directly. So the last place in the user land is not NTDLL. It's inside the syscall exe. So we can clearly see that this program do a syscall by itself. Okay, so now back to the hacker side. So we can still try to evade the detection on direct syscall. So to deal with the static analysis, we can replace the syscall instruction with some keyword and replace it at runtime. So this is called the egg hunter in the syswhisper tool. So the syscall instruction will only appear at runtime. So you won't scan syscall instruction when you use static analysis. And to deal with the dynamic analysis, we can use the original syscall gadget inside the NTDLL. So after setting the correct XSN, we can call the address of the syscall instruction in the NTDLL and jump into the NTDLL. So that should make your code stack look more normal, just like other normal program. Your code stack will get into the kernel from the NTDLL. Okay, so now you see that this is like a never-ending battle between the EDR and the attacker. So you can, the blue team can try to detect this again, and the hacker will bypass it again, and again and again. Yes. Okay, so for the next evasion, the attacker tried to patch the ETW. So the ETW is an event tracing tool built into the Windows, and it has different kinds of provider for different events, and it is very helpful for the to the blue team. So normally, if the attacker wants to patch the ETW to disable its behavior, they will override the first few bytes of the ETW event write. So this function is responsible for sending an event to the provider. So typically, we will replace the first few bytes with the return instruction. So this will effectively disable the function because the first instruction in the function is returned, so they will do nothing. But in this malware, hook is applied to the ETW event write. And what they're trying to do is to filter out only a few events they want to filter out and leave the rest the same. So you can see in the screenshot below, the function here is the hook on the ETW event write. And here, there is a if condition before coding the ETW event write for. And it will do the normal event writing behavior only if the event descriptor are not these three values. So these three values are the attacker trying to hide. They don't want the EDR to find out. So in this way, EDR can still see events from the ETW provider, but the event related to the malware has been filtered out. And this technique is something that we rarely see in other APT cases. And so in this case, they try to hook the ETW function. And in previous APT case, we often see they try to disable it completely. So this is kind of unique. So for the final evasion technique, the attacker tried to do PPID spoofing while spawning a new process. So PPID spoofing is a technique trying to fake the parent of the process. So for example, we can see in the screenshot here, the PPID spoofing process. This is a simple program that will spawn the notepad process directly. But instead of spawning, you can see that instead of spawning under the PPID spoofing program, the notepad is actually spawning under the LSAS. So by doing this, the attacker can try to make the blue team confused and may trace the wrong source. So they may try to find out what LSAS do and maybe try to scan the memory of the OSAS, but they will find nothing. So PPI spoofing usually have two ways to do it. So the first way is that we can specify the PPID in the parameter of create process. And according to the Microsoft DAO, we can specify the proc thread attribute parent process. By supplying this, we can set the PPID directly. So basically, this is a feature in the Windows that you can specify the parent of the process when you create a process. And for example, the word fault exe, you might see it before. And when this process will appear when your program crash. And this workflow exe will be created as the child process of the program when it crashes. So this is a normal behavior. There's something, some process will spawn under other one's process. So the second method to do PPID spoofing is to call another API named create process with logon W. So this API is actually it will do a RPC call to the seclogon RPC. And in this RPC, you can specify the PPID when you do the RPC call to the seclogon. So under the hood, the create process with logon W actually get the PPID parameter from the TEB of the current process. And then it will supply the PPID as the parameter to the RPC. So what we can do is that we can simply modify the PID in the TEB. And after modify it, we can call the create process with logon W directly. And now the newly spawned process will have their PPID whatever we want. So this technique is actually implemented in a tool called the malsec logon. And the author also write a blog about this. So if you are interested in this, you can see this. Click the link. See the link below. Okay. So here we see that the malware actually use the second method to call the create process with logon W to do the PPID spoofing. So when we look at the process using tools like Process Hacker or Process Explorer, the parent of the newly spawned process will look like the SVC host, which is not actually. So the second method is actually quite rare, and we also haven't seen this kind of method used in a while before. So to detect the PPID spoofing technique, we can use the Microsoft Windows kernel process, ETW provider. We can use this ETW provider to get the events. And the events generated from this provider will record a field called the execution process ID. And this field records the creator of the process instead of the parent of the process. So these two are different. So if we see a program has conflict between the process creator and the parent process, so there might be a PPID spoofing technique here. But be aware of the false positive, like the word fault we mentioned before, because this is a legitimate usage of the PPID spoofing. So now we see that parent process, by specifying the parent process, is actually a feature in the Windows. So parent process are not necessarily equal to the process creator. And if you want to trace the source of the program of a process, you should look at the creator of the process instead of the parent of the process. And when you do the PPID spoofing using the create process, the creator will be the one who called the create process. And we can use this to identify the real creator. But in the case when we do PPID spoofing using a create process with logon W, the creator will still be the SVC host. So in this case, we need to also look at the logon event to correctly trace the real source for the process who create the process. Okay, so finally, the malware will deploy Cobalt Strike as backdoor and connect back to the C2 server. The attacker here used two kinds of beacons in this case. One is the SMB beacon, and the other is HTTP beacon. And they work like a master and slave, whereas SMB beacon will connect to the HTTP beacon using a name pipe, and then HTTP beacon will connect back to the C2. And we actually can do a search on the name of the name pipe and find out that which endpoint is infected by Cobalt Strike. So in the screenshot on the top, we search for the pipe name, and then we get a list of all the endpoint that was infected by the Cobalt Strike. Okay, so finally we will look at our last APT case. So this is quite a simple case that the attacker tried to send phishing email to our client. You can see in the image that, but this is written in Chinese, so I translated some of them on the left. So basically, they're trying to pretend to be the blue team and ask the client to install the EDR in the attachment. They spend many effort to provide reason on why the client must install this EDR. So doing some basic analysis on the attachment file, we see that the EDR installer in the attachment is written in Python and packed by the py installer. The py installer is a famous tool to pack Python program into the Windows P executable. And this is a loader that will run to embedded binary. And one of the embedded binary is the original EDR installer, and the other one is the backdoor. So they actually contain the real original EDR installer, and they actually run it. The malware will run the EDR installer. So you can see that the malware is trying to act normal and run the original EDR installer, and the malware thinks that user won't notice anything because EDR is actually installed, right? But after the EDR installed, it immediately called the malware drop next to it. So this is kind of funny. And we see that this loader also used to pack other programs like the 7-zip, and with exactly the same code. So we're guessing that this is some kind of tools that can automatically add backdoor into a program. So the second layer of the loader is also written in Python. And after doing some regular VM detection to evade detection of sandbox, it decrypts a Cobalt Strike stager in memory and use create thread to run it. So it's like a normal malware. And the final payload is a Cobalt Strike stager. And we'll connect to the C2, the 139. The IP start with 139. Okay. So finally, in conclusion, we see that even the EDR installer can be used as a phishing bait. And this time, there is no winning lottery or payment reports attached. This time, the attacker is trying to tell you to install a security product while trying to hack you. Yeah. Okay, so this is at the end of my talk, and here is some takeaway. So first, we see that the attacker trying to, in the first APT case, the attacker trying to do API hooking on the EDR. So it is also important to protect the memory of the EDR from modification from the user LAN. And second, we see that BYOVD is being used commonly in the APT case. And to avoid it, we can also turn on the blacklist to block the commonly abused drivers. And next, we see that direct syscall is the most common way to bypass API hooking nowadays. And if there is a syscall instruction inside a program, then there might be a problem. And next, we also see a PPID spoofing case. So the parent process is kind of like a feature in Windows. You can specify whatever you want, but the parent process is not necessarily equal to the process creator. So if you want to trace the source of the process, you may want to look at the process creator. And finally, we also see an interesting case where attacker try to phishing as EDR. So the trust of the EDR can also be used by the attacker. So we should be aware of that. Okay, so here's my talk. Thank you, everyone.
Thank you so much. Thanks, Wei-Chieh, for the session. Just we have some time for maybe one, maximum 2 questions. Anyone? Yes.
Beside the blacklisting method for BYOVD, is there other types of telemetry that could be gathered from the endpoint via Sysmon or other tools that can give indication to that going on in the event an attacker changes the signatures or hashes of the blacklisted drivers?
Thank you for the question. So that's a great question. So mainly we will use blacklist to block the drivers, and as my knowledge, there's no simpler way to other than that, and because when you have a vulnerable driver, then anyone can bring that driver and exploit and get into the kernel. And once inside the kernel, they can do anything they want. So the simple way is to add it to the blacklist. And the Windows nowadays has the options default in its settings. So by default, it will turn on and it will update the list to the vulnerable drivers.
Thank you. Any last question? Yes.
So you mentioned modifying the etc host file to disrupt communication with the EDR. Does it help to have like a secondary monitoring solution like Sysmon was mentioned, or Trend Micro, something collecting information on when that file's modified?
Okay. Yes. So monitoring for the etc host is also a way to avoid, but maybe try to be careful that some the administrator will also try to modify the etc host to set something. So they should combine some other indicator to determine that this is a malicious activity to modify the etc host. Yeah.